Oh, so I said I would finish in practical one. So, I mean, what we can see here, I think you should have read through it. And so I don't think it has any complications, to be honest. What I'm introducing here is two types of residuals that, could have been introduced before the generalized Pearson statistic and the deviance statistic, because after all, they are sort of the building blocks of them. And so, you should be thinking of, the deviance is a generalization of the residual sum of squares. And so, that's the sum of the residuals, essentially, of the squares, the usual ones, the raw residuals. And then, if you think of the deviance as that, then it makes sense that it can be also written as the sum of squares of deviance, of some kind of residuals, right? And then same idea with the generalized Pearson statistic, because after all, the generalized Pearson statistic is a generalization of the the variance estimate in the normal linear model. And in this model, this estimate in the linear model, what it is nearly equal to is sum of squares of raw residuals as well, right? So then again, there is this analogy. Okay, and so there is a result here that tells us, the asymptotic behavior of these residuals under the small dispersion asymptotics, and this sort of agrees with the small dispersion asymptotics for deviance, right, and the generalized Pearson statistic, because if you take the squares, add them up, and so on, then you get chi-squared on n minus p degrees of freedom. Yep. Okay. So then, what this gives us is that we can standardize the two different residuals and get that if the model is correct and under these asymptotics, then you should be getting more or less a standard normals, yeah, for those. So we can have normal QQ plots, and and then the Cook's distance is just similarly computed to before, and so on. I mean, so really, I guess the point here is that we cannot use the raw residuals anymore, because they in a generalized linear model, they will not have constant variance, right? And having constant variance is precisely the key to having these diagnostic plots, right? Because under the assumption that your model is correct, you have this, at least in the linear model, you have this constant variance. And so what you can do is precisely to plot things to identify whether actually the variance is constant or not. That, of course, doesn't imply that the model is correct, but at least it tells us that that bit of the model is correct. And so, that's regarding the second moment. The other thing to check is the normality. So that's why you have the QQ plot. So that's why, you have several diagnostic plots that if you read them at once, then they give you more or less an idea of whether your normal model is correct. And in this case, we need to somehow get something that has constant variance. And this is what we just introduced, right? Okay, so please do unmute yourselves if you have any questions, because in the practicals, I do expect more participation than in the theory lectures, or at least you're free to have that participation.
Excuse me.
Yep.
As you mentioned it, could I ask a quick question? So I wasn't expecting a practical today for some reason. Even though I thought the practicals were on Wednesdays, but I guess that was just me being mistaken. So which days are the practicals on?
So they alternate.
Okay. So it just didn't alternate in week one.
Yes, they didn't. So what I did was the first two sessions were theory, because I wanted to introduce all of the GLMs before.
Yeah.
actually being sort of behind and in the practicals.
Yeah.
So I mean, I must have said this at some point, but yeah, maybe it was a bit confusing. Sorry, at first.
Okay, so from now on, it's going to alternate, but presumably we're going to have to do two in a row at the end. Because is it true there's 12 practicals in total?
Yeah. So I think I would pay attention to whatever announcements I make at the very beginning, because I generally anticipate what's going to happen in the next one. I mean, it's not a clear cut. I can't say that we'll have exactly 12 practical sessions. So we may have 11 and a half, if you like.
Okay.
So I will, generally speaking, I will anticipate, I will announce what's going to happen.
Okay.
But yeah, more or less the idea is that they alternate, unless I say the contrary, basically.
Great, thank you.
Yeah.
Well, I'm afraid I'm going to go and do the practical, but thank you very much.
Okay, sure.
I had a question. I had a question about practical 1, and on page 7.
Okay.
So question 4 about the effect of 1 year's increase in the age. Is this like additive or multiplicative increase?
What's the estimated effect of 1 year's increase in age on the average number? Yeah, I mean, this is multiplicative. Yeah.
Okay, I was just a bit confused by the way it was written down.
Yeah. I mean, that's multiplicative. Yes. Yeah, I guess you mean the answer in itself, right? Because I mean, the question.
Yeah, the way was the answer. Yeah.
Yeah. Yeah. Okay, fine. I could be slightly more specific, but yeah. Okay. Yeah. Okay. If there are no further questions for practical 1, I will go into practical 2. Okay. So practical 2, what we're going to see in this practical is the binomial regression, which is also known as logistic regression, and we'll introduce model selection as well in the last bit. Okay, so what we have here is data showing 2 types of seeds and 2 types of extracts. And so we wish to investigate the sort of interactions between these 2 different variables, which are going to be factors. Okay, and the data, as you see here, is the number of seeds that have been germinated. So I expect you to have sort of checked these things, that you're happy with these things. So it's literally a matter of copying, but please do sort of try to understand line by line. Let me just, so what I'll do is, you can stop me as I'm copy pasting.
Oh, hi.
Yeah.
Hi, sorry, can I ask a question, please?
Yeah, of course.
Yeah, I think so in the first practical, sorry, for the scale location plots, could you reiterate what a good one looks like? Is it that there is a flat trend, or that there isn't a flat trend?
You mean, of course, in the Poisson, right, model?
Yeah.
Okay. Okay, so I mean, it's not only the flat trend that matters, because it could have been that you have some sort of say like a kite shape, right? Here, so it could be that the average is still 1, but actually goes up and down and goes down and up. So clearly there would be a pattern that is telling us that the variance is actually much larger towards the middle and then smaller towards the sides. That's that's extremely uncommon in Poisson data. So what tends to happen in Poisson data, because before I go into what is common in the Poisson data, but that would have an average of around 1 for every value. And of course, it wouldn't mean that the fit is good, right? So it's not only that we want the flat trend in terms of the red line, but we also want it across sort of every point in the predicted values, right?
Yeah.
So I mean, to me here, it just looks reasonable. I mean, again, I think I said it last time, that this is not rocket science, diagnostic plots. So as long as it doesn't look, as long as you cannot spot out a very clear violation of the, sort of uniform cloud, then you're probably good to go. Because also the normal QQ plot looks perfectly fine. The Cook's distance, you have 1 maybe that is too, slightly worrying. In general, this doesn't look too bad. So if you go back, I mean, the first one and the residuals versus fitted and the scale location are very related, of course. And if you go to the residuals versus fitted, that looks again like a uniform cloud, right? More or less. So that seems perfectly fine.
Thank you. So just to check, for the Poisson, because the variance can be different, we had to standardize. And so the residual versus fitted, the top left one, isn't of any use. Is that right?
Isn't?
It's not useful because we have to standardize the residuals in the Poisson regression. Is that?
Yeah.
Okay. So the top left one is just essentially useless.
Yes, but so you shouldn't. Let's see. Actually, you are right. That is the raw residuals, isn't it? It does look to me as it could be raw residuals. Yes.
Okay.
Let me see. Just a sec. Yeah, but the variance does seem quite constant in that. So let me just check.
Is one maybe the Pearson residuals and one the deviance ones? Is that not it?
Yeah. So I mean, I would. Let me see. Let me just try to. So to be perfectly honest, I don't remember what residuals are there, but it doesn't look, if they are raw residuals, so I mean, I can definitely check this for next time, but if they are raw residuals, then they don't look too bad, so clearly. But of course, if they are raw, then you shouldn't be looking at that. As in, the fact that they are good doesn't necessarily mean that you can trust that in any way.
Okay. That's perfect. Yeah, thank you very much.
Yeah, sure. I'll try to remember to check that. Sorry, I don't have a pen with me. Okay. Let me maybe just write it down somewhere here. Okay. So talking about the second practical, yeah, okay. So we copied sort of this first bit, this second bit. So we're looking again at the influence of these two variables in the germination. And so there is a change in the practical, actually. So in fact, I don't have the new, so I'm not looking at the new version clearly, the one that I compiled just a minute ago. Am I? Seed extract. No, I am. Yeah. Okay. So I am. Yes. So there is, there is a new line here, and it's that the seed is also not a factor by default, as the data comes, and so that's one that we need to make a factor. So I mean, there may be small typos in the practicals, but given that you're supposed to be working this out beforehand, then something as simple as this, I would expect you to sort of anticipate that you need to change this. So you make these two factors, and then we can have some sort of ANOVA type of analysis. And what we have done in here as well is just to write the proportions, okay, rather than just the number of germinated seeds out of all of the seeds that we planted. And this is because for the GLM function, when it comes to the binomial family, there are a few ways in which you can introduce the data, but the most common one is through introducing the proportions, okay? So you need to create a new column there. And then even before the GLM, applying the GLM function, we can do some plots here, some interaction plots, some descriptive plots, exploratory analysis here. And what you see is these two graphs. So if there is someone who's not comfortable with any of them, please shout out now. So the interpretation of these, I think, is pretty clear, right? And it's that, these are the marginal effects. So with the first sort of vertical line, what you get is essentially, the mean of the proportions for seed B, irrespectively of the extract that was used, and same idea for the A, and then the same for these guys for the second vertical line. So that one disregards the seeds, okay? And then when it comes to the interaction plot, again, we have some mean of the proportions, but this one is a bit, so this one is not the marginal one, but rather, you fix the A, you fix the extract one, and then you take the mean, and then the same idea for the 4 points that are being joined here by the lines, and then you plot them out. So, if you look at this, you would say, well, clearly, seed A, regardless of the extract, so I'm looking at the left plot, seed A, will give rise to much more germination than B, regardless of the, well, at least marginally speaking, and then extract 2 will also be better in general, regardless of the seed. Yeah, so marginally, I guess. With the proportions, what this tells us is that, for extract 1, the germination is more or less the same, while extract 2 really has an effect on, well, it has an effect on both because it's clearly raised the line for both, but it has a much more, a much stronger effect on A than it does for B, right? So actually, it's not true what I said, yeah. So there is a catch here, and it's that to compute these two plots, so the means of the proportions, this really is the mean of the proportions, yeah. Why am I saying the catch is there? Well, because the proportions will come from different ends, so from fields that have different number of germinated seeds, and so it really doesn't make sense to take the average of these proportions, right? We should be weighting them by the ends, then taking the sum, so we're really taking the sum of the y's, and then dividing by the total sum of the weights, yeah. So that you really get an idea of, you're averaging out the effect for, once you fix the A, or fix the A and the extract, sorry, the seed and the extract, yeah. So we'll see in a bit that actually this plot is a bit different in reality, yeah. So this is what is written here in the answers. Okay, so if we fit the binomial model, then...
Hi, sorry, could I just ask?
Yeah.
So previously there you said, yeah, so those plots aren't valid because they're weighted differently, or they're sort of weighted wrong when you take the mean. Would all of this modeling be equivalent if, like, right at the start, you add all the y's and n's together in each group?
So, I mean, we haven't really. So you mean just for the plots, yeah?
Well, just I mean, when you do the binomial regression and just as you interpret the data, just by looking at it, is there any sort of reason to not have like the first, so all the A1s, you just got a sequence of sum out of the total.
Yeah, so you can do it. You can do it either way. So it's equivalent.
It is equivalent
as long as you do it rightly. So what do I mean by that? So if you, so let me jump. So let me just go here then, because that answers, the answer to that is here basically. Well, as in the answer, as in implicitly. I mean, so it's this line of code. There's this argument here of weights equal to n that is doing. Well, what that is doing is just sort of multiplying. Okay, so I'll answer that in a second. So let me just maybe go through this first, and then it will make sense, the answer. So, if we look at the proportions and weight them up by the number of germinated seeds of each sort of combination of the factors, then we assume this is binomial, or we could have written, this as a 1 over this here, so that it fits the way I introduced the EDF, the corresponding EDF. And so essentially, what, and I'm sorry I couldn't see your name because I don't have the cameras here. So what you asked essentially is whether one can sort of aggregate the values, that come from precisely the same combination of factors. And indeed you can, yes, because after all, what that's going to give you is still a binomial model. And if you look at the likelihood of the two models, so the one in which you aggregate and the one in which you don't aggregate, then they are exactly the same likelihood. So it will give you the same coefficients, basically, and the same inferential procedures. So you can do that. And they are equivalent because we're using these weights as weights, basically. So if you hadn't added this here, then it would have taken every point as equally important, with the same weight, and then it wouldn't have been equivalent to use the aggregated results. Yeah.
Yeah. Okay. Thanks.
Okay. Yeah. Okay. And just again, as in the usual binomial model, then we look at the the logit. The logit of the probabilities, and then we model that. Yeah. So we model that, including interactions here. And we have the usual corner point constraints. Yeah, so we have identifiability. Okay. Okay.
How exactly does it work with the value of n? Because like in the R says the dispersion parameter has been taken to be 1.
Mm-hmm.
And I thought for the binomial family you have like m is 1 over phi.
Mm-hmm. So what you get in the binomial family, in the binomial regression model, is that you have these weights, the AIs, and those can change, right? With these weights. So those are the ones that you can. So those are the ones basically that we are introducing here as weights, and then the dispersion parameter is actually 1 in that case. So it's not the dispersion parameter in the terminology of exponential dispersion families.
Oh, okay. Oh, yeah. You said it already. Sorry, I was confused.
yeah, exactly. So this is the dispersion parameter in the terminology of the GLM.
Okay, great. Thank you.
Yeah. So just, I mean, in any sort of programming language, what you have is data, and so always think that this is the statistical model rather than the probabilistic model, which is the EDF. Okay.
Should the weights be 1 over n then?
Yeah, I mean, here is,
So this just understands that it has to sort of invert them once it's got them.
Yeah, I mean, it's a matter of how you call, each thing, but yes.
Okay.
So here, weights are just 1 over what we call weights, yes.
So can I just clarify?
Yeah.
So for each of our, say, extract and seed combinations, we're fitting a binomial model with a special, say, Pij to all of the data that we have for that specific combination.
That's not what we're doing, but that is equivalent to what we're doing, yes.
Oh, so what we're doing here is we're actually aggregating all of the data for a specific combination first and then plugging it in.
No, sorry, then I misunderstood what you said. So that is what I said is equivalent to what we're doing, but it's not what we're doing.
Oh, so we are not aggregating before, because then we'd be losing a huge amount of data. Just to check. Okay.
We're not aggregating, yes.
Yeah,
So
okay. Just to check. Okay, that makes a lot of sense.
We're not aggregating, and this is why we have the K index here that is varying through all of the data points that have seed I and extract J.
Yeah.
Okay, but it would be again, so it would be equivalent to aggregating all of the K.
Sorry, it is, so it isn't equivalent. Right?
It is, it should be, yeah.
But if you aggregate everything, then you only have, say, 4 data points.
Yeah.
But that means you lose a huge amount of data, right? Or
you do, but you also gain it through. So this is the game of the meaning of the dispersion parameter. So the dispersion parameter is nearly 1-to-1 with the sample size, especially.
So it does also cancel out and match up again.
Exactly. So somehow you can absorb it into the dispersion parameter, and then you will be will be swapping large sample asymptotics by small dispersion asymptotics, basically.
I see. Okay. I see.
That's so. I think there is. So I set an exam question that was similar to this, or that somehow I wanted to explore this idea. So it wouldn't be from last academic year, but the previous one, and I think it was question 1 actually in the exam. Let's see. Yeah, so I think either I explored that question or that idea, or there is something very close in line with that, basically.
Okay. Yeah. Perfect. Thank you very much.
Sure.
When you say it absorbs into the dispersion parameter, which dispersion parameter are you talking about? The GLM one or the EDF one?
I'm always, okay. I generally talk about the EDF one because I don't need to say exactly how it does come into play in the GLM.
Okay, thanks.
It looks like there's a free parameter K defining Pijk. Would you be able to clarify that, please?
Yeah, so K is just the index, so it's here, so it's the experiment, is here, this one here.
Yes, but when you define logit Pijk, it equals mu plus alpha I plus beta j plus gamma ij, but there is no K on the right-hand side?
Yeah, because the K is the experiment, it's the experiment for a fixed combination of seed and extract. So you may have several of these experiments, but they should all have the same probability parameter.
In that case, are you saying that each Wij prop ijk goes like the binomial you've given, or is it the sum goes like the binomial you've given?
The sum of the guys with the same ij, you mean?
I mean, in the previous line, the sum over k, the sum from k equals 1 to capital Kij goes like something.
Sorry, I'm afraid I cannot see any sum here.
Oh no.
You may be looking at a different version of the practicals from last year.
Oh, well, there we go. That's it then. Sorry.
Yeah. So in that version, I was given precisely this aggregated version of things.
No, thank you. Sorry.
Yeah, no, that's okay. It's fine. I changed that for this year.
So does it take the errors of the different experiments as being different, or does it take the errors of, does it not aggregate them at all? Does it treat them all as independent of each other?
So as long as they are modeled as independent, what will happen is that the likelihoods are equal. So you will, if you compute the likelihoods for the aggregated version and for the non-aggregated version, then you'll see that because of the exponential, they sort of aggregate naturally, if you like. So you can do whatever. So this will not aggregate them. I mean, firstly, it doesn't matter if it does or not, but it will not because you have these degrees of freedom. Yeah. So you see here in the degrees of freedom, you get 20. So there are 21 data points. And so this is the null deviance corresponds to the model with just the intercept. And so clearly this is not aggregating. But again, the likelihood is exactly the same as if you had aggregated, and you would get the same fit. So you would get different degrees of freedom, but then you would be using small dispersion asymptotics rather than large sample asymptotics. I'll let you think about this a bit. Okay, we should.
Sorry, can you explain the corner point constraints? What they have to have this value of 0?
So I'm afraid with that I'm going to have to refer you to because we have very little time, and this is already from linear models. So I refer you to the notes basically from statistical modeling, if you want to take a look at that. So this is just a very, very common thing to do, which is so that you avoid identifiability issues, basically. And it's a completely standard thing. So if you Google corner point constraints, then you'll see there will be discussions about that. It's just because we have 7 pages left for a few minutes, and that is a prerequisite of a course. I'm sorry. Okay. So no, we have a bit more than 7, but anyway, yeah. Okay. So, checking whether it is a good fit basically means a goodness of fit test. Goodness of fit test is simply, checking your deviance. So you have your residual deviance, degrees of freedom, and then it's just a matter of computing the p-value, right? So the p-value tells us that the value of the deviance is a bit too large for what we expect on a chi-squared distribution on 17 degrees of freedom. And so it means that we have a poor fit. Yeah. Okay. Still, if we assume, that we're happy with this, then there is a fair question as to what is the interpretation of each of the model coefficients. So, I mean, it's just the usual interpretation for logit function. So we're looking at, if you look at the value, right? So this is the value of the, sorry, I haven't copied this. I don't think I missed anything. So, we have this coefficient here, and that coefficient is, of course, if you look at your model above, then it should be clear what it is, right? So it's just simply when you take I and j to be 1, both of them, then you get mu because of a corner point constraints, and so then it's just the logit function of the probability of seed A and the extract 1. And probably an easier interpretation is just saying, well, let me invert this logit function and take the x bit, so the logistic function of this minus 0.56, and this is what we have as an answer here, I believe. Yes, so it's the probabilities. So that's a bit easier to interpret. Yeah, the probability of germination for seed A and the extract 1 is 36%. That's a bit of an easier interpretation. And so I guess the point here, in addition to talking about what I just said, is that any additional parameter is always with respect to this mu, right? So it's always an additional, so it's an increase or a change basically in the log odds, rather than it being an absolute value. So it's a relative value essentially. Yeah. You can compute the absolute values as I do here. Yeah. And then it's just a matter of aggregating, well, adding up the mu and the, say, in this case, alpha to hat. Yeah. Okay. Any questions about this? Okay. So ANOVA, when we have factors, as we do here, we can have this ANOVA tables. And so the ANOVA tables, what they will do is essentially, to add, so I mean, this is again a prerequisite. So this is from linear models. And so it's the same idea as in linear models, but rather than using the residual sum of squares, you just use the deviance to get the table. And so we start with a null model in which we have a intercept, and then we start sort of adding variables to the extent that the last model we consider is the one with interactions. Yeah. And so they are incremental, by the way. So they're never compared to the first one, but rather, they're just incremental, and we add 1 and 1 and 1, and then it's compared to the previous fitted model. So that's why the degrees of freedom are 1 in every time. Yeah. And so I guess I'm saying this so that you can interpret the p-values correctly. Yeah. Yeah, and that's pretty much the answer to this question. And so you can you can fit this auto model without interactions. So the one we fitted before, so the one I have fitted here with this star, is just a product. And so this product, what it means is just to have all of the possible combinations of these two guys, both individually and also interactions wise. Yeah. While if we have a sum, then we have only the sort of individual variables rather than interactions. And that corresponds precisely to the penultimate model being fitted here. Yeah. So you can check the difference in the deviances. Well, I mean, okay, I'll let you, I mean, these things should be simple here. Yeah. I guess I just want to go through the practical in case you want to stop me at anything, but this is what this is saying. Yeah? So just take the difference of these two, and then what you're doing is essentially the last line, you'll get the p-value here in the last line of the ANOVA test. Okay, so surgery data, we have some tumors, so data of tumors from different patients. And we have a number of variables under consideration, some of them being factors, some of them just being continuous variables. And, we wish to predict, we wish to find the predictive factors for this survival of the patients. Okay, so there is a subtlety here, and it's the stage variable. So the stage variable is ordinal, and this is something that I explain here. So if you have any questions, just stop me. But yeah, that's one thing to point out. And yeah, so you can have a fit. So I'm just going to go basically through this without really explaining much, so that you can pause me at any point. We'll try to explain a bit less than this. What's wrong with that? Okay.
Excuse me.
Yep. Yes, go on.
I was looking at your website, and it doesn't seem like, for me at least, that the version with the solutions has been uploaded. I can't.
Yeah, it's not there. It's in the announcement in the model.
Oh, okay. Okay, sorry. Thank you.
That's okay. Yes, I'm assuming that everyone who's attending the live lectures is on Moodle, because in theory you shouldn't be able to get the link otherwise. Right, what's wrong with this? Okay, I see. Yeah. Okay, so output, can you summarize the effect of this on the odds of dying? So I mean, this is this is just the same as before, right? So what we, yeah, okay. So just what time is it? Sorry, so it's a bit late. If you just stop me on anything that you want to ask about this practical. I mean, we can, I guess maybe we can leave this model selection for the next practical in case you have any questions. Although there is nothing to be done other than checking that you understand the code. So now, do you have any questions about surgery data section, in which, you know, we introduce basically forward selection and backward selection. Hopefully the sort of notation is clear. So what we're doing is just starting with with a null model, and then adding one by one different variables, and up to the point in which we sort of have all of those that we can add, basically. So if p is smaller than n, then, you know, that's as many as we have as p. And then if p is larger than n, then we stop in n, so that we can, so that the model is still a reasonable model. Yeah. Otherwise, we wouldn't have any. We would have, you know, infinite solutions to the fit. Okay. And then the same idea in backward selection. So we have, you know, the full model, and then we start, we begin sort of removing variables. And so, you know, here this function, this step function, will precisely do this for us. So we've chosen to do it forward. Trace one means that we'll get output. But you know, if you have any questions about this and you're sort of going through the practical, then it's just a matter of taking the help function. Yeah. So if you go to step, then you go to the arguments, and then you've got trace, and then it gives you a brief description of it. Okay. And so we get this table, and you know, we have the different options of adding variables, you know, different deviances and AIC values, and then you can go, you know, you start sort of, well, you proceed as I said before, and then it gives you a selected model. Yeah. Okay. Any questions about this bit? Okay, so the confidence, maybe I should make a comment about this. Confidence intervals obtained through this, are they valid? So for those who did statistical modeling, they may know the answer already. If not, then that's fine. That's not, I mean, if you've seen linear models, then you may have seen it, but I guess it's not necessarily a prerequisite. I mean, this is a slightly more advanced knowledge. So what this regards what is called inference after model selection. And it's a subtle point, but it's a very important point. And it's that you cannot use the same set of data for selecting a model and for developing or for building inferential procedures for the selected model. Okay, what do I mean by that? Well, if you have your data, then you choose your model, and it doesn't matter through what procedure you choose it, but you end up with a model, and then now you take this model and you think, well, this is great, this is my model, and now you go and for instance here build confidence intervals for the coefficients of the selected model, but you do so, of course, with the data that you had initially. Yeah, so that's illegal. Yeah, that's not. You cannot do that. The reason being that this confidence. Well, so this is okay. So let me explain. I mean, it requires a couple of minutes. You should go back to the definition of a confidence interval. So a confidence interval only makes sense from a frequentist philosophy of statistics, and this is the following. So a confidence interval is a random interval that, if you repeat the experiment again and again and again and again, will give you that the desired coefficient, or the coefficient that you're looking at, is in that interval with a certain, for a certain proportion of time. Yeah, which is the one that it should equal the level that you chose. Yeah, it should be, or in line with the level that you chose. So it really looks at frequencies, right? So this is the frequentist understanding of statistics, and the first problem with these confidence intervals is that because you created them after the model selection, then it could be that every time you repeat the experiment, and repeating the experiment really means, if we're talking about the same set of data, then it really means including the selection of the model. Then it could be that you select a model in which you don't have the variable that you're now looking at a confidence interval for, right? So then is then the coefficient of interest, is it in the interval? If there is no interval for it, then what's the answer to that? I mean, there's of course no answer to that. So it really, conceptually doesn't make sense to there are no frequencies to be defined here. But even if you say, well, okay, let's just look at the coverage of the confidence intervals when I repeat the experiment. For those experiments that actually do have the confidence interval that I'm interested in, so for the coefficient whatever coefficient I'm interested in, so you're conditioning basically on having selected that coefficient. So if you look at the coverage of such intervals, right, so you look at the frequencies basically, again, then it will turn out that actually the frequencies do not match the level that you set at first. And this is because these confidence intervals will not be taking into account the variability that there is when you select the model. Okay, so they are overconfident that they know the answer. So they're overconfident that they know, in what region the coefficient is. Okay, so we'll go back to this point at some point and do an experiment, but you can check it with the linear model, for instance. So you can take the linear model, then do this, and choose, not the intercept, but choose some parameters, or look at maybe the first linear model that we fitted. Take one of the coefficients of your choice, then do model selection. Take those experiments that had that coefficient that you're interested in. Check the confidence interval, whether it contains the true value or not. Compute the frequencies. So do this many times, and then compute the frequencies. And then you'll see that it is overconfident. Okay, so you can check this by hand, basically, what I'm saying. But the reason, the conceptual or the theoretical reason behind it is that again, these confidence intervals do not include the variability of a model selection, so they're too narrow, basically. Okay. All right. So I basically sort of finished the session here, but I'm happy to stay for a couple more minutes